Hi everyone, welcome to the channel. In this video, we'll learn about how decryption is done in a Hill cipher. In the last video, we saw how encryption is done in a Hill cipher. We saw with an example of the plain text PAY. So for the plain text PAY, for the given key, we saw that the corresponding cipher text was L, N and S. So in this video, we will take the same cipher text L, N, S and see how we have to convert it back to the plain text using the same key. So to learn about how decryption is done using a Hill cipher, we need to know a lot of basics on the linear algebra. So first thing is how to find the determinant of a matrix. What is the meaning of determinant of a matrix? So the simple way to find out the determinant of a matrix is by taking the top row elements and its corresponding minors. So take the first element of the top row, multiply it by its minor. Then subtract the product of the second element and its minor. Okay, so you take this first element of the top row, multiply it by its minor. Take the second element of the top row, multiply it by its minor. So you would be subtracting both. So you continue to alternatively add and subtract the product of each element of the top row with its respective minor until you are done with all the elements of the top row. Let's see that with an example. Let's say you have a matrix like this, a 3x3 matrix. This is a 3x3 square matrix which contains these elements. Let's see how to find out the determinant of this matrix. So we are concerned about the elements of the top row, 17, 17 and 5. We need to take each of the elements of the top row and multiply it with its minors and then add up all of the results together. So this is how we would be doing it. Take the first element of the top row. The first element of the top row is 17. The corresponding minors for the element 17 is 18, 21, 2 and 19. So for the element 17, multiply the minors. Okay, so you have 18 into 19 minus 2 into 21. Okay, so after doing this, multiply this result with 17. Okay, so first find the minor element value and then find out the product of that minor element value with 17. Similarly, the next element in the top row is 17. For 17, the corresponding minors are, so how to find out the minors? Leave out, just eliminate this the column in which 17 is present and the row in which 17 is present. So we have to eliminate or delete this row and this column. After doing that, the corresponding elements are 21, 21, 2 and 19. So multiply 21 with 19 and subtract it with the product of 21 into 2. Okay, so you get 17 is multiplied with 21 into 19 minus 21 into 2. Same way, take the last element of the third row. Okay, so take the last element of the first row. So you have 5. Delete the corresponding row and column of this element. The corresponding row of this element is this row and the corresponding column of the element 5 is this column. After leaving out or eliminating or deleting this particular row and column, the corresponding minor for the element 5 is 21, 18, 2 and 2. So multiply this with this, that is 21 with 2 and then multiply 18 with 2 and then subtract the result. So 21 into 2 is 42 minus 18 into 2 is 36. 42 minus 36 would be 6. So that is what is calculated here. Then you have to multiply this product with the element 5. Okay, so going on further like this, we get 17 into 300 minus 17 into 357 plus 5 into 6. Remember take note of the minus sign here. For this first element, the sign would be 17. For the second element, the sign would be, for the first element, the sign would be plus. For the second element, the sign would be minus. For the third element, the sign would be plus. For the fourth element, if there is a fourth element in the matrix, it would be minus and so on. So this is how you calculate the determinant of a matrix. Determinant is nothing but a scalar value which is found out by using the minors and the top row elements of the matrix. The next thing is how to find the multiplicative inverse of a number using extended Euclidean algorithm in modular cryptography. So we are doing arithmetic mod 26 operations. All of our arithmetic operations are performed mod 26 in this Hill cipher. So if you have to find out the multiplicative inverse of a number mod 26, then you can make use of the extended Euclidean algorithm. For this, you create a table which contains 7 columns, namely Q, R1, R2, R, T1, T2, and T. Initially, T1 is assumed to be 0 and T2 is assumed to be 1. And the formula for calculating T is T1 minus T2 into Q. Okay. Now, what is this R1 and R2? Assume that the value which you want to find out, the question is of the form B mod n. Okay, so here 26 is your value for n and 23 is the value for your B. I want to find out the multiplicative inverse for B. So the value of n is copied into R1 and the value of B is copied into R2. Then divide R1 by R2. Do R1 divided by R2. When you do R1 divided by R2, the quotient which you get is put in the column Q and the remainder which you get is put in the column R. T1 is assumed to be 0 and T2 is assumed to be 1. So you enter that values. So when you divide 26 divided by 23, the quotient is 1 and the remainder is 3. So that is put. And T is calculated as T1 minus, that is 1 minus, 0 minus T2 into Q. T2 is 1 into 1. So 0 minus 1 would be minus 1. So that value is entered in the column T. The next step is, it continues in the same way, where in the second iteration, copy the values of R2 and R from the previous iteration to the columns R1 and R2. Say in the first iteration, the values of R2 and R was 23 and 3. Copy it to the column R1 and R2 in the second iteration. Similarly, copy the values of T2 and T to the columns T1 and T2 in the second iteration. So I have copied 23 and 3 to R1 and R2 and 1 and minus 1 to T1 and T2. Next, follow the same procedure. Divide 23 by 3. When you divide, you'll be getting the quotient as 7. Put that, insert that into the column Q, and the remainder would be 2. Insert that into the column R. And then here the value of T is T1 minus T2 into Q. So 1 minus 1 into 7. You would be getting minus 1 into minus 1 is plus 7. So 1 plus 7 would be 8. The value of T is calculated. So you would be proceeding in the same way. In the third iteration, the values of R2 and R is copied into R1 and R2, and the values of T2 and T is copied into T1 and T2. Then divide 3 by 2 and insert the quotient in the column Q and the remainder in the column R. Then find out the value of T using the formula T1 minus T2 into Q. So the third iteration completes. This goes on and on. This will continue till the value of R1 becomes 1 and the value of R2 becomes 0. Okay. And then when you reach that step or that iteration, then the value which is stored in T1 would be the multiplicative inverse for your 23. Okay. So when you go on further, you get all these values. In the fifth iteration, the value of R1 becomes 1 and the value of R2 becomes 0. And so the value which is stored in T1 would be your multiplicative inverse for 23. The multiplicative inverse for 23 is minus 9, which is a negative value. If you want a positive value as multiplicative inverse, then whatever value of n you use the value of n as 26, right? Add up 26 to minus 9 to get the positive value for multiplicative inverse. So you have to do minus 9 plus 26 to get the positive value for your multiplicative inverse. Okay, the formula which you have to use for doing decryption in Hill cipher is, to get the plain text back, we have key inverse into C mod 26. Okay, so you have to find the inverse of the key here. Whatever key, we know that already we have seen, we are working with symmetric cryptography. Same key will be used by both the sender and the receiver. So we need to use the receiver has to use the inverse of the key and multiply it with the cipher text which it has received in from the sender, and then perform a mod 26 operation on the result to get back the plain text. So the formula which is used for decryption is K inverse multiplied with C and perform modular 26 operation. So here, how to find the K inverse of the matrix K? K is your key matrix. How to find the inverse of the key matrix? So inverse of a matrix is nothing but K into, it is defined by K into K inverse is equal to K inverse into K is equal to I. That is, if you perform K into K inverse, you should get the identity matrix. Identity matrix is nothing but a matrix which contains all zeros except for the main diagonal which contains all ones. Except the main diagonal which contains ones, all other elements will be zero in an identity matrix. So if you multiply the matrix K with its inverse, you should get the identity matrix. That such type of matrix is called the inverse of a matrix. So here the formula which you have to use for finding the inverse is 1 by determinant of K into adjoint of K. You have to find the determinant value of K. You have to find the adjoint of K for finding the inverse of the K matrix. So what we are going to do is determinant. We are going to find the determinant value of K. Already we have seen what is determinant and how to find the value of determinant. So determinant value of K, it is, since it is 1 by determinant value of K, we are going to we have converted it into determinant value of K inverse. So 1 by determinant of K is represented as determinant of K inverse, and then we have to multiply it with adjoint of K. So first we take the key matrix and find the determinant value of K for the key matrix. Our key matrix is this one. This is the same key we use for Hill cipher encryption also. So now we find the determinant value of K. The determinant value of K is, so we take the top row elements and find out the product value of its minors, and then we multiply 17 with the value which we have got from its minor. So here we have 17. Here the minor for the element 17 is 18, 21, 2 and 19. So we multiply 18 with 19 and subtract it from 21 and subtract it from the product of 21 with 2. Okay, so the calculation is shown here, and the final value which we get for determinant of K is minus 939. We are doing modular 26 operation, mod 26 operation. All arithmetic operations are performed mod 26 here. And so when we do minus 939 mod 26, we would be getting a negative value of minus 3. Already I told, when we get negative value in this mod 26 operation, we can, if you want a positive value, we can do minus 3 plus 26. That is a shortcut. So minus 3, 26 is your value of n. Whatever value of n you have to add it with that value of n. Here we are doing mod 26. So we are adding it with 26. So minus 3 plus 26 gives you a positive value for determinant of K mod 26 value. So minus 3 plus 26 would be 23. So the value of determinant of K mod 26 is 23. The next step is, we have found out that the value of determinant of K is 23. We need to find out the inverse of 23. To find the inverse of 23, we have to use the extended Euclidean algorithm. Just now we saw how we have to formulate the tabular column and how we have to calculate. So we found out the modular inverse of 23 as minus 9. So all operations are performed mod 26 here. So when we do minus 9 mod 26, we will be getting the result as minus 9. When to convert that negative value to positive value, we have to add 26 to it. We will be getting minus 9 plus 26 as 17. So the value of determinant of K inverse, the value of multiplicative inverse for the value 23 is 17. Okay. So the next step is, this is the This is the formulation of the extended Euclidean algorithm. The algorithm proceeds with the value of n stored in R1 and the value of b stored in R2. And as long as the value of R2 remains greater than 0, we would continue our procedures for calculation of the quotient and the remainder and store it in the appropriate columns. And finally, when the value of R1 is equal to 1, the value stored in T1 would be your multiplicative inverse for the given value B. So next step would be, when we have found out key inverse, the next step would be to find out the adjoint of key K. This is our key K matrix. So we need to find the adjoint of K. For that, we have 3 steps. First step is to find the transpose of the key matrix. Transpose is nothing but just interchange the rows and columns. The first row, 17, 17 and 5 becomes the first column of our transpose matrix. So here you can see 17, 17 and 5 is there in the first column. The second row contains 21, 18 and 21. This second row will be changed to second column in the transpose matrix. Third row would be changed to third column in the transpose matrix. So finally, we have got our transpose matrix, and this is the first step in finding the adjoint of the key K. Next step would be to find the minors for our transpose matrix. So minor has to be calculated for each element of our transpose matrix. And this minor of a particular element Aij is nothing but we need to delete for any element Aij where I is your row and j is your column. We need to delete the ith row and the jth column and find out the determinant of the corresponding matrix we have got. Say, for example, our transpose matrix is present here. We need to find out the minors for this transpose matrix. So here, for the element 17, the corresponding minors are 18. So for the element 17, delete the first row and the first column. So the first row is 17, 21, 2. The first column is 17, 17 and 5. Hide the first row and the first column. When you hide the first row and the first column, the corresponding elements you have got is 18, 2, 21 and 19. Find out that these are the minors for 17. Okay, so find out the determinant value for these elements. So how to find out? 18 into 19 minus 21 into 2 would be the determinant value for these minors. So when you do 18 into 19 minus 21 into 2, that would be the value for 17. That would be the minor element value for the element 17. Same way for the element 21, hide this column in which 21 is present. Hide the second column and the row in which the 21 element is present. The corresponding row is the first row and the second column. So when you hide that, the remaining elements which you get is 17, 2, 5 and 19. Find out the determinant of those elements by doing 17 into 19 minus 5 into 2. Okay, so that will be the minor element value for the element 21. You have to do that 17 into 19 minus 5 into 2 and place it in this position where 21 was present. Same way we need to do for all of those elements. For the third element, let's say for the third element 2, hide this particular third column and the first row. 2 is present in the first row, so delete that first row. 2 is present in the third column, so delete that third column. The remaining elements which you get is 17, 18, 5 and 21. Find out the determinant by doing 17 into 21 minus 18 into 5. That is placed in the position where that result is placed in the position where the element 2 was present. So when you do all of that, you would be getting the minors for the transpose matrix KT. So the final elements which you get is this 300, 313, 267 and so on. This is your minor matrix. The third step in finding out the adjoint of a key matrix K is you need to find out the cofactor for our minor matrix. The cofactor for any element Aij is defined by where I is your row and j is your column. You have minus 1 power I plus j into determinant of the minor matrix. Already we have found out the minor matrix. You need to, so simply said, what you have to do is just append, these are the signs for the various rows and columns. Okay, so how we have got that is by using this -1 power I plus j. If your I is first row, if your element is in first row and first column, you have 1 plus 1 is 2, -1 square would be +1. So you have a plus symbol in the first row and first column. If it is first row and second column, you would be getting 1 plus 2. So 1 plus 2 would be 3. -1 cube would be -1. So you have a negative sign in the first row, second column. So that is how it proceeds. So simply put, if you have calculated the minor matrix, simply append these signs. These are the scalar values for a 3 cross 3 matrix for your for finding the cofactors. So simply append these signs with the with your minor elements. So plus, minus, and plus. So since we have a minus in the second column, 313 becomes -313. We have a minus in the second row, first column, we have a minus, and in the second row, third column, we have a minus. So 357 and 252 becomes -357 and -252. So finally, we get this matrix. This is our final adjoint matrix for the key K. So this is how you calculate the adjoint matrix. So we have now our determinant of, so we are working towards calculating the value of key inverse. To find out the value of key inverse, we found out the multiplicative inverse for determinant of K, and we found out the adjoint of K. Now we have to multiply these two to get our, multiply these two and do a mod 26, because all operations, once you perform determinant of K, once you find out determinant of K, you have to do mod 26. Once you find out this multiplied value, you have to do mod 26, because all our arithmetic operations are performed mod 26 here. So our determinant of K inverse value is 17, and our adjoint of K is this matrix we have just now found out. Just to do a normal scalar multiplication of 17 with this matrix. 17 into 300 would be 5100. 17 into -313 would be -5321. 17 into 267 would be 4539. So in this way, we have done a normal scalar multiplication and got this matrix. Now we have to do mod 26 operation on this resultant matrix. When you do the mod 26 operation for negative numbers, you have to remember it is not the same way for positive and negative numbers. 5100 mod 26 is, you will do in the normal way. You will divide 5100 by 26, and the remainder of the division operation will be the value returned. So the remainder of doing 5100 divided by 26 is 4. So that is placed in the resultant matrix. But for negative numbers, when you do a modular operation on negative numbers, you have -5321 mod 26. So how will you do? Do it in the normal way as though you do it for a positive integer. Do 5321 mod 26, but then attach a negative sign for the result. Okay, so here when you do 5321 mod 26, the result would be 17. When you do with positive 5321, the result would be 17, but this is -5321, so I have attached -17 here. Similarly, when you do -4284 mod 26, do it as though it is a positive number. When you do 4284 mod 26, the result you would get would be 20. So then attach a minus sign with the result. Next, if you get a minus symbols, if you get minus sign in the result, again you have to do mod 26. Again, you have to convert it into positive values in the result, because we cannot work with negative values. So since we are doing mod 26 operation here, to convert all of these negative values into positive values, you have to add 26 to the negative result. That will give you the positive value of the result. So you have to do -17 plus 26. Here you have to do -20 plus 26. Here you have to do -11 plus 26. Here you have to do -9 plus 26 to convert them to positive values. Then only you will get the actual value of key inverse. So when I do all of that, -17 plus 26 would be +9, -20 plus 26 would be 26 minus 20 would be 6. So when you do all of that, you get this value of key inverse. Finally, we are done with finding out the value of key inverse. So our formula for decryption in Hill cipher is key inverse is multiplied with the cipher text, and then we have to do mod 26 operation on the result. So we have found out the value of key inverse here, then you have to multiply it with the column vector for the cipher text. Our cipher text was L, N and S. You have to convert it into its numerical equivalent. Okay, A is mapped to 0, B is mapped to 1, C is mapped to 2 and so on. Z is mapped to 25 and Y is mapped to 24, etc. So in that way, L is mapped to 11, N is mapped to 13 and S is mapped to 18. Okay, so we have got the value of key inverse, multiply it with the value of the cipher text. When you multiply it with the value of the cipher text, do a normal matrix multiplication. When you do a normal matrix multiplication, 4 is multiplied with 11 plus 9 is multiplied with 13 plus 15 is multiplied with 18. Add up all of the product values together. The product of 4 and 11 is added with the product of 9 and 13, and then it is added with the product of 15 and 18 to get your final column vector value, to get the result of your matrix multiplication. Similarly, 15 is multiplied with 11 plus 17 is multiplied with 13 plus 6 is multiplied with 18. So these are the mappings I have shown you. You can see here that L is mapped to 11, then N is mapped to 13 and S is mapped to 18. You do the addition operation of all the products. 4 into 11 would be 44, 13 into 9 would be 117, 15 into 18 would be 270. When you add up all of them together, you would be getting 431. So similarly, for the second row, when you add up all of them together, you would be getting 494. For the third row, when you add up all of the values, you'll be getting 570. Now perform a mod 26 operation on each of the values in the resultant column vector. When you do 431 mod 26, the result would be, the remainder of the division operation would be 15. When you do 494 mod 26, the result would be 0. When you do 570 mod 26, the remainder would be 24. Then when you convert all of them to its alphabetic equivalent, you would be getting the value of 0 as A, the value of 24 as Y, and the value of 15 is for the alphabetic character P. So finally, we have converted the ciphertext LNS back to our plain text PAY, and this is how decryption is done in your Hill cipher algorithm. Simply put, we'll be calculating the value of key inverse, multiplying it with the ciphertext, and then performing a mod 26 operation to get back our plain text. Now, when you examine the strength of the Hill cipher, since we make use of a larger matrix here, it is able to hide more frequency information. It hides single letter frequencies and double letter frequencies very well. It is able to completely hide all the single letter as well as 2-letter frequency information. And if you take 3-letter or 4-letter frequencies, the frequency of occurrence of such words are very less. And so Hill cipher is very much strong against a ciphertext only attack. But then Hill cipher can be easily broken for a known plain text attack. What is the meaning of known plain text attack? Sometimes the analyst may be able to capture one or more plain text messages as well as their encryptions, or he may know that certain plain text patterns will appear in a message. For example, if your file is encoded in PostScript format, it will always begin with a particular pattern. Or if you have an electronic funds transfer message, there will always be a standard header for that message. So all these are examples of a known plain text attack. Say in the case of Hill cipher, if you have a M cross M Hill cipher, and if the attacker has M plain text ciphertext pairs of length M, then let's say we label the pairs as, the plain text pairs as P1J, P2J up to PMJ, and the ciphertext pairs as C1J, C2J, and CMJ. And let's say the attacker doesn't know the key matrix K. So what can be done is, two M cross M matrices can be defined with X is the set of all the plain text pairs and Y is a set of all the ciphertext pairs, and a matrix equation can be formed as Y is equal to Kx, where Y represents the matrix pair for your ciphertext and X is the matrix pair for your plain text. So if X has an inverse, if the plain text matrix has an inverse, then we can determine the key as key is equal to Y into X inverse. Or if the matrix X is not invertible, then a new version of X can be formed with additional plain text ciphertext pairs until an invertible value of invertible X matrix is obtained. So this is how we can see that Hill cipher is more susceptible to a known plain text attack. So that is all about Hill cipher encryption and decryption. Thank you.